Yeah, that's why I don't really. It's just.
All right, we will get started. It's 11 o'clock. So some announcements. Your Chapter 6 Achieve homework. We'll finish Chapter 6 in class today. So the Achieve homework is due on Wednesday before class. My office hour today is going to be different than it normally is. So it's at 4 p.m. and it's remote. So if you go onto our Blackboard page and click on Blackboard or Class Collaborate, then you'll join that video chatting software that we have through Blackboard, and I'll be on there. So feel free to join anytime during that hour if you have questions or anything you want to review. And then Wednesday, my office hours are at the normal time, so 1 p.m. upstairs in my office. And then that feedback form that I mentioned last week, that's still open, but it closes at the end of the day today. So please respond to it if you haven't already. About half of my total students, I have 2 sections, half total have responded. So I'd like to hear from more students. I want to get a better idea of how everyone is feeling about the class and about your learning. So it should only take a few minutes. So if you haven't already, please fill that out. You can find the link in the most recent Blackboard announcement. Okay, so we are finishing Chapter 6 today. At the very end of class on Friday, we introduced or talked about the idea of an enthalpy change. So this is the change of energy or the heat transfer for a process that's carried out at constant pressure. And so it can be measured using a calorimeter. And then these are reported in units of kilojoules per mole of reactant used or product produced. And so usually this value is given after a chemical equation. So here's the reaction to form water, so forming H2O from its elements, H2 and O2. And this reaction, when this occurs, releases 572 kilojoules of energy. So this is the enthalpy change associated with this chemical reaction. So that's kind of how we see the values. And it's important to note that delta H, so change in enthalpy, is a state function. So remember, we talked about state functions as being different than path functions. Path functions depend on the process of getting from the beginning to the end. It's a lot of chatting. Let's quiet down. It's distracting to the students around you. Thanks. So enthalpy is a state function, meaning it does not matter what process is taken from starting material to products, as long as you have a process to go from starting material to products. So delta H, change in enthalpy, depends only on what the reactants are and what the products are. As long as you know what molecules are reacted or decomposed in some way and what molecules are formed, you can calculate change in enthalpy using different reactions that decompose those reactants and produce the products. So here's an example on this slide. This image is on an energy scale, so energy is increasing as you go up the slide. So standard enthalpies of formation can be used to calculate the enthalpy change of a reaction, of any reaction. And so this reaction here, where we're decomposing NO2 and forming N2O4, so NO2 is our reactant, N2O4 is our product. In this reaction, we're not actually forming O2 gas, N2 gas, and then producing the products. But we can use the change in energy from starting at the constituent elements that make up both of those compounds to find the change in enthalpy of this total reaction. So we're decomposing NO2. Well, the decomposition, the enthalpy of decomposition of NO2 is a known value. This reaction is shown here. We're decomposing it into its elements. That decomposition is shown here. Excuse me. Where NO2 is a high energy molecule. If it's decomposed, it will release energy, and the elements are at a lower energy overall. So that's our decomposition of the reactant. And then if we're looking at forming the product, well, if we start with N2 and O2, and the energy to form the product, the enthalpy of formation is shown here. So it requires some energy to form the product from the elements. And so the enthalpy of reaction of this reaction here is the difference between these two. So that's shown with this lighter green arrow here. That's the enthalpy of reaction. So as long as you know the enthalpy to decompose the reactants and the enthalpy change to form the products, then you can find the change in enthalpy for that given reaction. And so we can use Hess's law, which essentially states that. And this blank is just any reaction here. Okay, so Hess's law we will use to essentially go through this process. So this states that the enthalpy change for any overall process is equal to the sum of enthalpy changes for any set of steps that leads from the starting materials to the products. So as long as you have reactions where you have starting materials as reactants and products as products, you can add enthalpies and find the enthalpy of reaction. So this was the overall, same as the last slide. This is the overall reaction we're looking to find the enthalpy of reaction for, the change in enthalpy for that reaction. Well, if you know the enthalpy of decomposition of the starting material, NO2, to form these two products, and you know the enthalpy of formation of N2O4, starting with these two products, then we can add those enthalpies together, and that gives us the heat of reaction. And it works out here because we have, in the first reaction, N2 as a product, and in the second reaction, N2 as a starting material. So those cancel out. Same thing with O2 gas. We have 2 moles on the right, 2 moles on the left, so those cancel out. So if we add these enthalpies together, we get the heat of reaction, because if we are adding these reactions together, canceling out what's present on both the product and reactant side, we get our overall reaction. Now, sometimes we have to manipulate the reactions that are provided. So if we have the enthalpy values for a reaction, we might have to manipulate that reaction. We'll do this on the next slide in this example. So we'll walk through this together. Our goal is to calculate the enthalpy change for this reaction. So 2 hydrogen gas molecules, 1 nitrogen gas molecule to form 1 N2H4 molecule. Now, we don't know the change in enthalpy for that reaction, but we know the change in enthalpies for 2 reactions that we can use to then find the change in enthalpy for our desired reaction. So this is provided data that we can then use to find the enthalpy change for the reaction that we don't know the enthalpy change for. And remember, Hess's law says that, we go back, the enthalpy change for an overall process is equal to the sum of the enthalpy changes for any set of steps that leads from starting material to products. So we will use these 2 reactions, make sure we're going from starting material to products, and then we'll add up the enthalpy changes. So first, we have H2 and N2 gas as our reactants. Well, of our two reactions that are provided, the second one has H2 and N2 gas as reactants. So we'll use this one, and let's just rewrite it. Keeping coefficients as is provided in the reaction. And then we'll state the enthalpy, change in enthalpy of that reaction, which is negative 92.4 kilojoules. Now, when we use this reaction, that gives us the H2 reactant, the N2 reactant, but now we have NH3 as a product, and NH3 is not present in our overall reaction that we have boxed at the top there. So we will use the other reaction provided in a way to both cancel out NH3 and show that N2H4 is being produced. Now, if you look at the reaction above, so now the first one with N2H4, N2H4 is a starting material. So if we were to just copy that right down, then we're not going to have N2H4 as a product. So one of the rules involving, or that Hess's law involves, that we'll talk about on a future slide, is that you can take a reaction like this one, the N2H4 plus H2 produces 2NH3, and switch starting materials and products. So now you'll have 2NH3 as your starting material, forming N2H4 and H2. So let's write that down first. So 2NH3 forms N2H4 and H2. So I'm flipping this around. Now for the change in enthalpy, if this reaction that's provided at the top there, the forward reaction producing NH3 releases 187.8 kilojoules. Then if we're doing the reverse reaction, starting with NH3 and producing N2H4 and H2, the change in enthalpy is the same value but opposite in sign, so positive 187. So that's one of the laws that's stated on the next couple of slides. Okay, so we've used both reactions here. Now we need to make sure that if we cancel things out, we are obtaining our overall desired reaction on the top there. So we see NH3, remember that's not present in our desired reaction. We have two NH3 molecules on the product side, and we have two on the reactant side, so those get canceled out for the overall reaction. Now the only other substance that's present on both the reactant and the product side is H2 gas. We have 3 H2 molecules, or 3 moles of H2 on the reactant side and 1 mole on the product side. So this 1 mole will be canceled out, and this coefficient becomes a 2. We're canceling out just 1 mole. So this is canceled out, and then this becomes a 2. So now with these 2 steps manipulated in the way that we've done that, switching that first reaction, we have 2H2 plus N2 produces N2H4. So we have our desired reaction. Yep.
Say you didn't cross off the hydrogen and then you just wrote that equation and then balanced it. Could you do that?
As long as your final one is the correct equation, that's fine. Yeah, no problem there. The only problem with that might be if you end up needing to multiply coefficients. This is another rule that we'll talk about. you would also need to multiply this value, and you would just need to know exactly which reaction you're multiplying the coefficients. So we have our desired reaction here. So that means that our change in enthalpy for this reaction is the sum of the change in enthalpies for the individual reactions. So the change in enthalpy for that reaction is 95.4 kilojoules. So we're just using Hess's law to manipulate known information to get information about the reaction that we're trying to understand better, trying to get information about. Yeah.
So, do you decide whether you add or subtract
These?
enthalpy, like based on the equation?
Yeah. So
you
whatever.
always add them?
Well, you'll always add them together, and you just need to make sure you have the right sign. So you always add them, but since that one's negative, we'll get a number that's lower than 187. Okay, so let's go through these rules for manipulating chemical equations. Rule 1, we've already done. If an equation is reversed, the sign of its enthalpy changes. So the first reaction here, we have nitrogen gas, oxygen gas forming NO. Its enthalpy change is 180.6. Now if we take NO gas and then produce N2 and O2, so the opposite of the equation shown on top, change in enthalpy is negative 180.6. So same number, different sign. This is what we used in our previous example. Another rule, when the coefficients are multiplied or divided by a factor, so we'll have to do this in some cases, then the enthalpy value is multiplied or divided by that same factor. So here's an example. This first reaction, we have calcium as a solid reacting with, let's say if we have 1 mole of calcium, then half a mole of O2 gas produces calcium oxide. If we then multiply all coefficients by 2, we have 2 moles of calcium, 1 mole of oxygen producing 2 moles of calcium oxide. Then the enthalpy change in this reaction is 2 times the enthalpy change of the original reaction, so this value here. So any coefficients that goes for multiplying or dividing, you multiply and divide the enthalpy value by the same factor. And then the next rule, we also use this in the previous example when reactions are summed. So when for the previous example, we added those 2 reactions together, canceled out what's present on both sides. We do the same thing here. So if we take carbon in diamond formed and add oxygen, that produces CO2, which has its own change in enthalpy. We take CO2 and form carbon in its graphite form and oxygen that has its own enthalpy. In these reactions, O2 is on the reactant side of one, product side of the other. CO2 is on the reactant side of one, product side of the other, so those get canceled out. We get carbon as a diamond forming carbon in graphite form, and its enthalpy of formation is the sum of the 2 reactions above. So negative 1.9. So we also use this in our example. Yes.
Those are 2 different equations.
Yeah, they are. Okay, let's do another example. I'll give you all like 2 minutes to get started, and then we'll go through it together. So we are calculating the standard enthalpy of formation. I'll give you a second. We're calculating the standard enthalpy of formation in kilojoules per mole of copper oxide. So we're forming copper oxide. We'll talk more about standard enthalpy of formation, but This is, in case you don't have it on your slides, we're taking copper as a solid in its standard form, oxygen as a gas in its standard form, and forming copper oxide. That's what you're looking for. Okay, yes, do you have a question? We don't have eye clickers today. Surprise. No, it's recording. Yeah. I shouldn't prepare any for today. Okay, so get started trying, and I recommend, here's one thing as you're getting started. Either start with your reaction that contains copper as a solid or copper oxide, and then use other reactions from there. Only reason I don't recommend starting thinking about oxygen is because it's present in two reactions, and so that will complicate things. So start with copper solid. You can write that reaction down and then try eliminating using others, or copper oxide. Either way is fine. I think when I go through, I'll start with the reaction that produces copper oxide first. So yeah, 2 minutes and then we'll go through it together. This one's a little different. So we need to we're doing this stuff as we make this reaction, and then we'll be able to cancel out the SO2.
And then that would also be
So,
or that would cancel out one.
And then, so yeah, I would like use all of these.
I'm just curious about how to, like, do we have to divide the topic?
Okay, I got it. Is that okay?
Yeah.
Okay, yeah. Will you actually?
Or do you email it?
Either way. Okay. I'll remember if you give it to me in person.
Okay, I'm gonna figure out her name.
Okay. I'm gonna go through it. Yeah, quick question. Okay, let's start going through this. So again, you could start with the first reaction, copper solid, that has a copper solid reagent, or start with the last one. Either way is fine. There's multiple ways to go through this process. I will start with this last one, so the reaction that forms our desired product. So copying everything down, we have copper sulfide, oxygen gas, and that produces 2 moles of copper oxide and 1 mole of sulfur dioxide. And the change in enthalpy for this reaction is negative 527.5 kilojoules. Okay, so we're starting there. We need to use other reactions to cancel out sulfur dioxide, because this isn't present in our desired reaction, and copper sulfide, because it's also not present in our desired reaction. We also need the reaction that gives us copper as a solid as our reactant. So we could take the first reaction and add this in. So 2 copper solid and sulfur. And the change in enthalpy for this reaction is negative 79.5 kilojoules. So you should always write this off to the side, because you need to sum them together. So far with these 2 reactions, we can cancel out copper sulfide. So that's all set. But we still have solid sulfur that needs to be canceled out and sulfur dioxide that needs to be canceled out. So we can use that second reaction, but we'll have to use it with the products as starting materials as products. So we'll flip the sign of the enthalpy and have sulfur dioxide forming solid sulfur and oxygen gas. And so that enthalpy change for this reaction is positive 297 kilojoules. And now we've canceled out sulfur dioxide. We've canceled out sulfur as a solid. And then we're canceling out 1 mole of O2 gas on either side. So we change that coefficient on the left to 1. So now if we add all of these together, we have 2 copper solid atoms, 1 atom of oxygen gas forms 2 copper oxide. And then the sum of the enthalpy change, so adding all of these delta H's together, is negative 310 kilojoules. Yes. We will. Yeah. Okay, we did a lot of steps already, adding all of these together, switching reactants and products. Questions on what we've done here? Okay, a lot of questions would end here. This question doesn't, because the question is to find the enthalpy of formation in kilojoules per mole of copper oxide. This is the enthalpy of formation of 2 moles of copper oxide. So if we want to find the enthalpy of formation of 1 mole, then we need to divide all of these coefficients by 2, and then divide the change in enthalpy by 2. So then we have 1 mole of copper sulfide plus 1/2 mole of oxygen gas. And this forms 1 mole of, not copper sulfide, but solid copper. 1/2 mole of oxygen gas, and that produces 1 mole of copper oxide. So the enthalpy change for this reaction is negative 155 kilojoules per mole of copper oxide formed. Yes. It is okay. Yeah. Yeah. You could divide or multiply multiple times because you might have to divide or multiply any of these to cancel out. If you have like more, if we had 2 SO2 products, then we would have to multiply this by 2 to cancel them out. If you divided the first one, but then you would probably have to divide the others to have, yeah, that would, as long as you are getting here, that should be fine. Yeah.
Don't check.
Oh, the behind you first, sorry.
When you do it this way, you still have one person whereas if you divided the first one to the last one, you would get that.
Then your values are probably off because this balanced equation is with a 1/2 there. Because there's only one oxygen in the product. So if we keep our coefficient of the product as 1, then we need 1/2 mole of O2 gas to have 1 oxygen on the left, 1 oxygen on the right. Yeah. With normal balanced equations, how we've done it in the past, how you balance an equation, we don't use fractions. It would be 2, 1, and 2. But for this equation, we need the coefficient of the product to be 1. Yeah. That was it? Okay, yeah. Other questions? Okay, so what we've shown here, this value is the enthalpy of formation of copper oxide from its constituent elements, and that's what our next section is all about. So, standard enthalpies of formation. So, the standard state of a substance is a state in which the substance is most stable at 25 degrees Celsius, which is 298 Kelvin, and 1 atmosphere of pressure, 1 atm. This is standard temperature and pressure. Room temperature, chemists define as 25 degrees Celsius, and 1 atmosphere of pressure, that's the pressure of our atmosphere at sea level. So the standard enthalpy of formation, which is, I don't know if yours is down here, but hopefully not, but that's delta H subscript F with that degree symbol. The degree symbol is explained down here. This means we're at standard temperature and pressure, so 25 degrees Celsius and 1 atm. This is the enthalpy of formation of 1 mole of a compound from its constituent elements in their standard states. So in that last example, we formed 1 mole of copper oxide from its elements, copper and oxygen, in their standard state. So copper at standard temperature and pressure is a solid. Oxygen at standard temperature and pressure is a gas in a diatomic form, so O2. Here's another example. If we're forming water, and we take its constituent elements, hydrogen and oxygen. Hydrogen in its standard state is H2 gas. Oxygen in its standard state is O2 gas. So to form water, that reaction has its own enthalpy of formation. Now, if you were thinking about the enthalpy of formation of H2 gas, well, that's the element hydrogen in its standard state. There's no energy associated with forming that element. So delta HF, standard enthalpy of formation of an element in its standard state, is 0. So H2 gas is 0, O2 gas is 0. In our previous example, we had copper as a solid as one of the elements. The change in enthalpy of formation of that is 0 because that's just the element in its standard form. So this next slide has a bunch of values. These are not values to memorize. These are values that would be provided to you. What you should remember is that elements in their standard state have a enthalpy of formation of 0. But these are some non-zero standard enthalpies of formation at 298 Kelvin. So, for example, Let's just look at sulfur dioxide. We took sulfur in its standard state, oxygen in its standard state, combined them to form sulfur dioxide, then 296.8 kilojoules of energy are released for every 1 mole of sulfur dioxide produced. That's what that value means. These are known values that, again, would be provided to you. Someone did these reactions. We don't need to do them again because the values are not going to change. We have the same element, same temperature and pressure. So these values can then be used to calculate the change in enthalpy of a more complicated reaction. Yep.
So besides these, the rest are zero?
No. These are just some that are non-zero. There are others. I just didn't include all of them. We're going to use them in a different way. These are just some that were provided that are, I think, the first table in the book, which is why I only included these. But if you needed any others, they would be provided. There's a lot more for a lot of different compounds. There are standard enthalpies of formation. So on the next slide, this explains how we can use these known values to calculate the change in enthalpy for an overall reaction. So the change in enthalpy for an overall reaction, we take the sum of the change in enthalpy of formation of all the products multiplied by the coefficient of each product, and then subtract the sum of the change in enthalpy of formation of all of the reactants multiplied by the coefficient for each reactant, and that will give you the standard enthalpy of formation of the reaction. So as long as you have the balanced equation and then the enthalpies of formation of everything involved in the reaction, then you can find the change in enthalpy for the overall reaction. Let's do an example. Next slide. So we will calculate the change in enthalpy of combustion. Do you have this equation on your slide?
Yeah.
Okay. So we will calculate the change in enthalpy of this reaction. So we want to find delta H for this reaction, standard temperature and pressure. Now we know from that table the standard enthalpy of formation of CH4. O2 is oxygen in its standard state, so that's 0. We know the standard enthalpy of formation of CO2 and the enthalpy of formation of H2O. Those are all provided in that table. So we'll use those values provided in the table and the equation on the last slide to calculate the change in enthalpy of that overall reaction. I'm going to rewrite the general equation. So change in enthalpy of a reaction. We take the sum of the coefficient, I think they labeled it as, coefficient for each product multiplied by the change in enthalpy of formation of each product So the sum of all of the products, change in enthalpy of formation multiplied by their coefficients, and then subtract the same thing but for reactants. So coefficient of each reactant multiplied by the change in enthalpy of formation of each reactant. So here we go, long equation. Now, maybe three things to always remember. One, you're starting with your products. So we add together the enthalpies of formation of each product first and multiply each enthalpy of formation by the coefficient. And then subtract the sum of the same thing for the reactant. So we start with the products. So we'll start with carbon dioxide. We have 1 mole of carbon dioxide, and we multiply by the standard enthalpy of formation of carbon dioxide. We can go back to our table. Standard enthalpy of formation of carbon dioxide is negative 393.5 kilojoules per mole. So it's in that table. That's the value that we'll use. So that's one product, and then we add the same thing for water. Now water has a coefficient of 2, so we say 2 moles of H2O times the standard enthalpy of formation of H2O, which is negative 285.8 kilojoules per mole. And those are only two products. So we're set with that first part of the equation. And then now we subtract, I'm going to move below, so we need more room. We'll do the same process, but for the reactants. So we form 1 mole of CH4, multiply by the standard enthalpy of formation. If you go back to your table, it's negative 74.81 kilojoules per mole. And then our second reactant is oxygen. We have 2 moles of oxygen. Its standard enthalpy of formation is 0 kilojoules per mole. So I'm writing it out here. In the future, if you want to just ignore it, that's fine, because this is going to be 0 for any element in its standard state. So now we can simplify what's in our first set of brackets. So 1 mole of carbon dioxide times its enthalpy of formation plus 2 moles of water times water's enthalpy of formation. This is negative 965.1 kilojoules. So all products, simplify that, we get this value. And then we subtract what's in the second set of brackets. So really just 1 mole of CH4 times its enthalpy of formation. So negative 74.81 kilojoules. And then if we do the subtraction here, we get negative 890.3 kilojoules. So again, we're using known values, enthalpies of formation of different molecules, compounds, to find the enthalpy change for an overall reaction. Yes.
Why for the method did you use 74.81 when on the table it's 74.6?
Because that's what I had in my notes, but you're right, 74.6. So I got these questions from 2 different resources, so they had a different value. So either way, we'll be fine. Okay, I don't think you have this in your notes. Oh, and I don't have it in my slide either. Oh shoot, that's a bummer. Give me a second. We're going to open up one more example, and we'll do that for the end of class. Okay, so same process, but different reaction. We have hydrogen sulfide and oxygen gas forming water and sulfur dioxide. So in the extra space that you have, it's not working, I guess I have to use red. You'll need these values and write down this reaction, and then calculate delta H of this reaction. I'll give you a couple minutes to get started and we'll go through it together. Sorry. There we go. And then if you have questions on this or the previous one, remember, the enthalpies of formation of the product minus the sum of the enthalpies of formation of the reactant. Okay, let's start going through this. So, same process as the previous example. Delta H of the reaction is the sum of the enthalpies of formation of the products times their coefficients minus the sum of the enthalpies of formation of the reactants times their coefficients. So, I'm not going to write out that general equation. We'll just start plugging in values. So, we'll start with water. We have 2 moles of water. And its enthalpy of formation is, oh, it's provided above. So negative 285.8 kilojoules per mole. And then we add the same thing for sulfur dioxide. We have 2 moles of SO2. Standard enthalpy of formation of SO2 is negative 296.8 kilojoules per mole. So that takes care of our products, and then we subtract. Same thing for reactants. So we have 2 moles of H2S. Standard enthalpy of formation is negative 20 kilojoules per mole. And then we have oxygen, which we'll just have as 0 because its standard enthalpy of formation is 0. So summing the first brackets, subtracting within the second set of brackets, we have negative 1,125 kilojoules. Released for that reaction above. All right, we will end here. We'll start chapter 7 on Wednesday. Don't forget that your next Achieve is due Wednesday as well.